40 millimeter. So pitch P is given. So when they give 60, you take this pitch, that is the longitudinal pitch and also the transverse pitch as 60 millimeter, and edge and end distances. This is the end distance and this is the end edge distance. You can take those values as 40 millimeter. So you don't have to worry about finding out those two values. Okay. Okay. Look here. So we have two plates. So one is of 18 millimeter thick and the other is of 10 millimeter thick, and we are trying to join them through a butt joint. Okay. So two plates of different thickness. Remember. So carrying the same force. And we have two lines of bolts. In each line, we have 3 bolts. So it is a double bolted chain bolting. Okay. So if you look in this portion, so because 10 mm thick and 18 mm thick will have a difference of 8 mm, through butt joint, you need to fill up this area by certain material, that is with the same steel piece. Okay, this is called a packing plate. So what is the thickness of the packing plate? 8 millimeter is the thickness of the packing plate. So as a result of the thickness of the packing plate, if the thickness of the packing plate is more than 6 millimeter, then the shear strength of the bolt gets reduced. Okay. So what it means, I hope you have the code book with you. Please open page number 75 of the code book. Please open it. So are you on that page? Okay. Come to the second column and go to 10.3.3.3 packing plates. So that says the design shear capacity of bolts carrying shear through a packing plate in excess of 6 mm shall be decreased by a factor beta pk given by beta pk equal to 1 minus of 0.0125 tpk. What it means is, when you find out VDSP on the left column of the same page, where VDSP equal to VNSB divided by gamma MB, so that VDSB value gets reduced. So by how much? So by certain percentage. So whatever value VDSP you get should be multiplied by beta pk to get a new VDSB value. Okay. So due to the result of the packing plate. If the packing plate thickness is less than 6 millimeter, then you don't have to worry about it. So presence of the packing plate does not affect the value of VDSP. Okay, less than equal to. Okay, now coming back to the problem. So if you look at the bolt, each bolt is under double shear. Okay, so we need to find out what is the bolt strength in shear and what is the bolt strength in bearing, and also we need to find out what is the tearing strength of the cover plate and also what is the tearing strength of the main plate. So least of those 4 values is the strength of the joint. Okay. So coming to the first case, shear. So the bolts are in double shear. Because of difference in thickness of main plates, a packaging plate of 8 millimeter thick is given. Okay. So the thickness of the packing plate is 8 millimeter, which is greater than 6 millimeter. So we have to give a correction for the value of VDSP to get the new value of VDSP. Okay. So here, as per 10.3.3 on page 75 of the code book, so beta pk equal to 1 minus 0.0125 tpk. So what is tpk? It is the thickness of the packing plate. So once you substitute that value, we are going to get the value of beta pk equal to 0.90. So once you have that 0.90, this VDSP value equal to this formula we have, and that value should be multiplied by beta pk. Okay, so here as usual, NSASB, we are going to assume that all those two shear planes are going to pass through the threaded area. So once they are passing through threaded area, NN will become 2 because of double shear, and A and B is the net area or the area of cross section of the bolt at the threaded level, which is equal to 0.78 divided by pi by 420 square. Okay, so substitute all the values, including that 0.90 for beta pk, you are going to get the shear value or the bolt strength in shear equal to 81.48 kilonewton. Remember, without this 0.90 for double shear for 20 millimeter diameter bolt, the shear strength of the bolt was 90.26, if you remember. 90.52 kilonewton. Because of this value, beta pk, which is equal to 0.90, so shear capacity of the bolt has reduced to 81.48 kilonewton. Okay. Therefore, what is the design strength of 6 bolts? If you look here, how many bolts we have? So we have 6 bolts on each side. So those 6 bolts should be considered. We should not consider all the 12 bolts. So for analysis and design purpose, we only consider half of the joint, and we are going to analyze our design for half of the joint, and the same thing we are going to replicate on the other side. Okay, so coming back to this, so for all the 6 bolts, the shear capacity of those 6 bolts is 6, that is the number of bolts, divided by 81.48, that is the bolt strength in shear. So we got the design strength of 6 bolts in shear equal to 488.88 kilonewton. So next, coming to bearing. So we are going to make use of this formula as per 10.3.4 on page 75 of the code book. So E by 3DO, 1 second. P by 3DO minus 0.25 FUB by FU and 1.0. So in this case, E is already given in the problem. So you don't have to find out what is E. So DO is the diameter of the bolt hole, which is diameter of the bolt 20 millimeter plus 2 as per table 19, page 73 of the code book. So after substituting the values, we got this value equal to 0.60. Similarly, P by 3DO minus 0.25. P is already given in the problem, which is 60. So we got this value as 0.659. So and FUB by FU equal to 0.975, and also the value should not exceed 1.0 in any case. So out of these 4 values, least value is the value of KB. Therefore, KB equal to 0.60. Okay. Now we need to substitute this value in this place. So when we substitute, so this is key. Thickness of the plate is key. If you remember the bearing value, so in the previous case, we used to have the 2 plates of the same thickness, is it not? So for example, if this is 18 millimeter, this is also 18 millimeter. Okay, this is 6 millimeter and 6 millimeter. So 6 plus 6 is 12 and 18 millimeter. Lesser of those 2 values should be taken. Okay, but in this case, we have 3 cases. So one is 8 millimeter and another is 10 millimeter plate, main plate, and also 6 millimeter and 6 millimeter. So least of these 3 values should be taken. If at all the plate fails due to bearing, then this 18 millimeter thickness plate is not going to fail by bearing. Instead, 10 millimeter thickness is going to fail due to bearing, because both of them are carrying the same force because of the lesser thickness for this plate. So this is going to yield or fail first as a result of bearing. So that is the reason why we should consider 10 mm thick for T value. So coming to this, see what is in this equation. So KB is already calculated. what is D is the diameter of the bolt. What is the T value? So T is the least of the following thicknesses. One is 18 millimeter, one main plate thickness. Another plate is 10 mm thick, and sum of the two cover plates is 12 millimeter. So least value for this is 10 millimeter. So that is T value. So substituting all the values in the equation for VDPB, we can get the value of VDPB equal to 96 kilonewton. So strength of the joint due to bearing, that is the design strength of the joint due to bearing equal to number of bolts multiplied by bolt strength in bearing. So 96 multiplied by 6 number of bolts, 576 kilonewton. Okay. Next. So these are the two possible ways a bolt can fail. One is due to shear, okay, and the other is due to bearing. Then another, and even plates can also fail, as we discussed in the previous classes. So that is, the cover plates can fail, and also main plates can fail. Okay, when it comes to the main plates, so what we must do is, we should not consider 18 millimeter thickness plate. Instead we should consider 10 millimeter thickness, because if at all any plate fails due to tearing of the plate, that is going to be 10 millimeter because of lesser thickness, is it not? So for that, the strength, if at all this fails, that fails along section 1-1. But for the cover plates, so section 2-2 is critical. So find out what is the design strength of this 10 millimeter thick plate at section 1-1, and also what is the design strength of 6 plus 6, 12 millimeter thick cover plates at 2-2. So we'll have two more values. So that's what I have done. I have calculated the values. Tearing of plates, that is rupture of plates. Section 1-1 is critical for main plate, and section 2-2 is critical for cover plate. So when I say main plate, I'm repeating, I'm considering the thickness of the thinner plate, not 18 millimeter thickness. So we have this formula from page 32, okay, under 6.3.1, where TDN equal to 0.9 FUN gamma ml. So what is AN? That is the net area of cross section of 10 millimeter thickness plate. Okay, so this AN I have substituted here. Okay, so what is B? That is the width of the plate, which is 200 millimeter minus 3DH, because at section 1-1 we have 3 bolt holes. So that is 20 plus 2 is the diameter of the bolt hole. Okay, 200 minus of this much multiplied by the thickness of 10 millimeter plate, that is 10 millimeter. Okay, that is AN value divided by gamma ml, which is 1.25. Convert the value into kilonewton through this 1000. Finally, we got the design strength of the main plate equal to 395.57 kilonewton. Okay. Similarly, the design strength of the cover plates. Same formula, same AN value is this, but as far as thickness is concerned, the thickness is 12 millimeter for the cover plates, because we have two cover plates, each of thickness 6 millimeter. So the total thickness of the cover plate is 12 millimeter. So substitute the values in this formula. So that is these values, and we get the rupture or tearing strength of the plate of the cover plates equal to 474.68 kilonewton. So we have found out the design strength of the joint with respect to the failure of the joint in all 4 possible ways. Okay, that means a joint can fail due to shear, and a joint can fail due to bearing. Then it can fail due to tearing of the main plate, and also it can fail due to tearing of the cover plates. Okay, so we have got 4 values. Out of those 4 values, take the least value. So if you come to shear, what is the value for shear? It is 488.88. What is the value for bearing? It is 576. So what is the value of the plate? Main plate 395.57. What is the value of the cover plates? 474.68. So out of these 4 values, least value is the design strength of the joint. Okay. So out of equations 1, 2, 3, and 4, okay, 3 controls the design. Therefore, strength of the joint equal to 395.57 kilonewton. Okay, that is the way you need to find out the strength of the joint. Next, we need to find out what is the efficiency of the joint. So for efficiency in case of chain bolting, if you look here, we need to consider only one pitch width. That is, this is 60 millimeter. So take half of it, 30 millimeter, draw a line like this. Similarly, on this side, come for 30 millimeter and draw a line. So the width of one pitch is 60 millimeter. And a figure is drawn for that portion here. If you look here, okay, this is 60 millimeter. So to find the efficiency, what we have to do is we need to consider one pitch width. Remember, one pitch width for chain bolting. For diamond bolting, of course, we are going to consider the whole joint. But for chain bolting, like this, it is only one pitch width. So coming to the shear, you know, shear value of bolt is 81.48 kilonewton. You remember? VDSB equal to FU by root 3 NNANB plus NSASB divided by gamma MB. And also we multiplied that value by another value called beta PK due to the presence of 8 millimeter thick packing plate. So through that we got this value. Okay, this is the shear strength of one bolt. Okay, so in this pitch, so we have 2 such bolts. Just try to pull this 6 mm width plate in this way, and these 2 bolts are offering resistance against that pull or push. So that's why the total strength of the bolt in shear is 2 multiplied by 81.48. This is number of bolts. So 162.96 kilonewton. Similarly, bearing strength of bolt per pitch length is 2 multiplied by 96. What is 96? It is the bearing strength of each bolt. You remember VDPB value we have calculated. Okay, 2 is the number of bolts, that is 192 kilonewton. Okay, so that is the strength per pitch length. Then tearing of plate. If at all this 60 millimeter width plate fails, it fails along this or along this. Is it not? Because this is a main plate, it fails along this direction. Okay, so what is the area? That is this 60 millimeter width minus diameter of the bolt hole multiplied by the thickness of the plate. So if you come to this formula, 0.90 AN FU divided by gamma ml. So where did you get this formula? You got this formula from page number 32, page number 32 under 6.3.1. Okay, where AN is the net area. So net area is pitch minus DH. In this section, pitch is 60 minus DH. There is only one bolt we are cutting in this way. So it is P minus 20 plus 2. T is the thickness of the thinner plate. We have 2 main plates, 18 mm and the other is 10 mm. So 18 mm plate is not going to fail. Instead, 10 mm is going to fail first. So that thickness should be considered. That's why I have taken 10 here, multiplied by FU 410. That is 410 is the strength of the plate material. Okay, 1.25. multiply that value by 1 by 1000 to get the strength of the plate, okay, at the critical section or at the weakest section, which is 112.76 kilonewton. Okay, so out of per pitch, out of equations A, B, and C, what is the strength? Least value. This is the least value we have. So out of here, equation A, 162.96. Equation B, 192 kilonewton. Okay. So tearing of plate, 112.76. So we are considering per pitch width, remember. Okay. Out of these three, least value is this one. That means C, equation C controls. Therefore, the design strength of the plate per pitch width is 112.76 kilonewton. So, by definition of efficiency equal to strength of the joint per pitch width, which is 112.76, divided by the strength of the solid plate of pitch width multiplied by 100. So we need to find out what is the strength of the solid plate per pitch width or pitch length. Okay. So again, make use of this formula. So AN is 60 multiplied by 10. 60 is the pitch. Okay. Pitch width multiplied by the thickness. So this gives the area of cross section of the solid plate. Okay. FU is 410 divided by 1.25 multiplied by 1 by 1000. So we got the strength of the solid plate as 177.12 kilonewton for one pitch width. Okay. So this divided by 177.12 multiplied by 100 will give you the efficiency. Therefore, efficiency of the joint is eta, that is equal to 63.66%. That is the efficiency. Is it clear to you? So this is over. Next, we'll go with the next problem. Anyway, I have not solved this problem, but I'm going to give you some clue, on how to solve this. Okay, just do it yourself. See, these are the truss members. Okay, this is a gusset plate. Okay, and all these truss members are meeting at this point, and everything, all those four members, this four members are connected to the same gusset plate of 12 mm thick. Okay. Next, we have two angles. One angle, ISA 75 by 75 by 6. You know what is an angle by now. Okay. 75 millimeter is the dimension of one leg. 75 is the dimension of the other leg. And 6 millimeter is the thickness of the angle. Okay. And one of the legs is connected to the gusset plate. Similarly, if you look here, yes, sir.
Sir, I think class is not recording, sir. I think class is not recording. Video is not recording, sir.
No, I'm doing that.
No, sir. The record caption is off, sir.
Oh. Okay, started there. We have this joint. Okay, four angle members are coming and meeting at this point. Okay, and those four members are connected to a gusset plate of 12 mm thick. So one of the members, again, all four members are angle sections. This is ISA 75 by 75 by 6. That means, so it is an equal angle. That means legs of the angle are the same, and 6 millimeter is the thickness. So is this. And when you come to these two members, so this member is subjected to 250 kilonewton. This member is subjected to 375 kilonewton. And what has been done here is have provided two angles. One is ISA 110 by 110 by 8. Okay, one angle. And there is one more angle we have provided behind this gusset plate. That means we are putting two angles back to back. Okay. And the backing of those two angles are attached to the gusset plate. Is it clear to you? Similarly on this, same two angles, and they are placed back to back. In between gusset plate comes. So this is a single angle, and of course this is a single angle, and this member is subjected to 125 kilonewton of tension, and this member is subjected to 125 kilonewton of compression. Okay, so let me go through the problem. The lower chord of a roof truss is as shown in figure. Okay, so this is the lower chord. In a roof truss, of course, there are top members, bottom members, and in between intermediate members within that, okay, which are inclined normally, and even there are some horizontal and vertical members depending on the type of truss we are using. And this is the bottom chord. Okay, so determine design strength of the bolt. We have two parts for this problem. Okay, and number of bolts required to connect the angles to the gusset. So assume M20 bolts means assume 20 millimeter diameter bolts and use ASP equal to 304 millimeter square and A and B equal to 245 millimeter square. So that is, they have given the diameter. Okay, sorry, they have given the gross area of cross section of the bolt at shank level, which is 340. At the threaded section, it is 245 millimeter square. So whatever value you want to use, you can use. So as I said, to be on safer side, I am using only 245 millimeter square and I am ignoring this part. And whenever you design a connection, so you should not care whether that member is subjected to compression or tension. You only consider the magnitude of the force. If you consider this member is subjected to a tensile force of 125 kilonewton, and this member is subjected to a compressive force of 125 kilonewton. So when you design these two members, so the design varies because you will have one set of procedure to design a compression member, another set of procedure to design a tension member. But when it comes to the design of connections, so you only consider the magnitude of the force, but not the nature of the force. Okay, so these sections are already designed and those members are given. We need to worry about designing only the connection. So the first part is design strength of the bolt. Here we have two types. See, when we provide a bolt here, okay, along this line, so each bolt will be under single shear because there is only one angle. So one of the legs of the angle is attached to the gusset plate. When you drill a hole, so then put a bolt. When you pull or push this member, so there is going to be only one shear plane between the back of this angle and the gusset plate. That means the bolt is in single shear. That is true even for this member. But when it comes to this member and this member, so this member has two angle sections, and also this member has two angle sections. So one angle is like this, and this thickness, I have shown these two lines, means that is coming, this is projecting outwards, perpendicular to the paper. Okay, that is the way you need to imagine. And there is one more angle behind. So when you provide bolts and try to pull this member after providing the bolt or push it, so there will be two surfaces, shear surfaces for each bolt, offering resistance against the shear failure. That means bolt we are providing here and also for this member is going to be in double shear. Okay, so here what you need to do is find out what is the strength of the bolt here as 20 millimeter diameter bolt, okay, in shear. And when it comes to bearing, so we have two thicknesses. One is thickness of this gusset plate, 12 mm thick, and also the thickness of the angle 6 millimeter. So for bearing, you must take lesser of these two values. So that is 6 millimeter. That way you are going to find out VDPB. So you will have the shear strength of the bolt, VDSP, and also you will have bearing strength of the bolt, that is VDPB. Take lesser of those two values as the bolt strength, or simply you can say bolt value. Okay. Once you have that bolt value, this force 125 kilonewton divided by the bolt value, that is the strength of each bolt, will give you the number of bolts. Okay. Once you have the number of bolts, provide those bolts in a single line. Say you got some two bolts. So provide one bolt here, okay, and one bolt here and one bolt here at the proper pitch and also at the proper end distance. Okay, in case you get three, provide them with proper pitch. That means with proper pitch means you have to be, the pitch should be greater than equal to P minimum and less than equal to P maximum. Similarly, you have to maintain the edge distance from this edge and also end distance from the last center of the last bolt to the nearest edge. Okay, so that way you need to provide number of bolts here. Similarly, when you come here, so this member is subjected to 250 kilonewton and this member is subjected to 375 kilonewton. Okay, but here they are given the same section, that is 2 ISA 110 by 110 by 8. That means, so two equal angle sections. So one of the legs is 110 and the other leg perpendicular to the paper is 110 and the thickness is 8 millimeter. Okay, we have two angles. Here, when it comes to the design strength of the bolt, both in bearing and shear, again you'll have to do once again the calculation. So when it comes to shear, here the bolt is in single shear. So you need to multiply whatever value, single shear value, with 2 to get the bolt value in shear. Okay, in this case the bolt is in not single shear, double shear. So find out the shear strength of the bolt. Next, bearing. So when it comes to bearing, so this is 12 mm thick gusset plate, and what is the combined thickness of those two angles which are placed back to back? 8 millimeter plus 8 millimeter, there is one more angle behind. So 16 millimeter should be compared with 12 millimeter of the gusset plate, which falls, gusset plate is arranged between those two angles. Okay, you take lesser of those two thicknesses. Here in this case 12 millimeter thickness is the one which is less than 16 millimeter thickness. That is 16 means 8 plus 8. Okay, so then you will have bearing value. You will have shear value. Here the bolts are in double shear. Find out the value. Next, find out the bearing value. Take lesser of those two values as the strength of the bolt or bolt value simply. Once you have the bolt value, then divide 250 kilonewton divided by the bolt value. Okay, and find out how many number of bolts you need and provide those bolts along this. Okay, similarly divide this value by the bolt value to get the number of bolts and provide those bolts along this line. Okay, so there is possibly there is one more correction. Okay, here they have given 125, 250, 250. Because they have not given that force as the ultimate load, you should take those loads as service loads. Okay, so multiply this by 1.5 multiplied by 250, 1.5 by 375, then divide that value by bolt value to get the number of bolts. Okay, not on 250, instead of 250 it is 1.5 times 250. So 1.5 is the load factor. That point I forgot to mention. Okay, so I hope this is clear to you now. Okay, number of bolts required, again I'm going to repeat, number of bolts required for this member is going to be 1.5 multiplied by 125. That will give you the design force divided by the bolt value. Similarly for this. So again, number of bolts required is going to be 1.5 times 250 divided by the bolt value. So that will give you the number of bolts here from here to here, and provide those bolts and connect to the gusset plate. Similarly, on this side, 1.5 times 375 divided by the bolt value will give you the number of bolts, and provide that many number of bolts from here, because we have this member and this member are separate, and there is a dividing line between these two. Okay, you have to provide a set of bolts here and a set of bolts here. I hope this is clear to you now. So we will go with the next part, that is called slip critical connection. Okay, whatever we have dealt with until now is the bearing type of connection. Bearing type of connection means, so there was a contact between the bolt, side of the bolt, and also side of the plates. So that means they were in contact and they were pressing against each other. Okay, in case of slip critical connection or slip resistant connection or friction connection, so what we do is, first, if we are trying to join these two plates through a butt joint and through two cover plates, and we don't want this bolt to get in touch with the side of this plate, still we need to transfer the force. So say, for example, this is subjected to F. This is subjected to a force of F. So for that, what we do is, again, we bring those two members face to face, that is a butt joint, and we are going to provide two cover plates, and we are going to make this of high power bolts. Okay, I have shown only one bolt here. So depending on the design requirement, there may be number of bolts. So bolts may be in one line or two lines. In each line, it may be 2, 3, 4. We don't know. That depends on the design. Okay. So here what we do is, after putting the bolt, we put the nut and we are going to tighten the nut to some extent. So once you tighten the nut, okay, this member, bolt member, is going to be subjected to tension because of the tightening. In turn, that applies compressive force on these two plates, on these two cover plates, that in turn applies pressure or force on this main plate. Similarly on this side, okay, once they are tight, if you apply some force from outside, so there is going to be some friction developed between the surface of the cover plate and the top surface of this main plate. Similarly on this side, similarly on this side, and similarly on this side. And that friction is going to resist the force applied on these two members externally. This is called friction type connection. So in this case, as I said, so this bolt and the side of the, that is side of the bolt and the side of the main plate are not going to be in touch with each other. Is it clear to you? So sometimes we may have to design slip critical connection or friction connection or slip resistance connection. Slip resistance means there should not be any slip. So whenever slip happens, then the side of the bolt is going to come in contact with the side of the plate. That becomes bearing type connection. Okay, so that's what it is. Let me read out the theory, and also I'm going to discuss a little bit what is given in the code book. Okay, and afterwards we are going to solve a problem on this. See here, when member forces are large and or where the connection length is limited, the HSFG, that is high strength friction grip bolts, are most suitable. That means here we are not going to use black bolts. So black bolts are of strength, say 400 Newton per millimeter square. We need to use HSFG of 8.9 or 10.8 or 10.9, wherein the ultimate tensile strength of the bolt is 1000 Newton per millimeter square if it is 10.9. If it is 8.9, it is 800 Newton per millimeter square. So through those bolts only you can tighten and you can apply compressive force. So any black bolts you use, they may fail. Okay. So we should not use all those black bolts or ordinary bolts. So here we are going to use HSFG bolts, that is high strength friction grip bolts. So going further, at service loads, the joints do not slip and hence they are called slip resistant connections under service loads. But at ultimate loads, these do slip and the joints behave like bearing type connections. When they slip, there is going to be contact between the bolt and the plate on the side. Then they behave like bearing type connections. Okay. So all those slip critical connections theoretically are not subjected to shear and bearing. Okay, they must have sufficient shear and bearing strength in the event of an overload that may cause slip to occur. That means in case of accidental slippage, that means if the friction is not adequate to resist the external force, then this plate and this plate are going to move towards each other, away from each other. That means the resistance is going to fail. Then in that case, it is going to become the bearing type connection. Okay. So that's why what we do is slip critical connections may be designed using factor loads or by using service loads. So all those slip critical connections theoretically are not subjected to shear and bearing. They must have sufficient shear and bearing strength in the event of an overload that may cause slip to occur. So in some designs, what we do is, even though we are going to design that as slip critical connection, we are going to check against bearing and shear also in case of accidental failure of or accidental slippage. Okay, then that becomes bearing. Then we have to make sure that even those two bearing and shear conditions are satisfied. So this part I'm going to skip, not much, while the slip resistance is based on a serviceability criterion. The design check is made for convenience using factor loads. However, the joint can slip and go into bearing at loads greater than the working loads, and hence the bearing capacity must be checked. So I'm going to explain once we get a problem. So before going further, please open the code book so that I can discuss something in the code book. So open page number 76 of the code book. Please open it, page 76. Are you there? So on 76, left column, 10.4, it says friction grip type bolting. Okay. So if you go to the next column on the same page, it says VDSF equal to VNSF divided by gamma MF. So what is VNSF? So just go below it. VNSF is equal to mu F NEKH FO. So all those values are given in the code book itself. Those values will be given. Okay, you need to make use of it. So coming to VDSF, as I said, which you need to find out, what VDSF is the friction strength or nominal shear capacity of a bolt governed by slip for friction. Okay, that is the basically friction strength of each bolt, you can say. Okay, that is VDSF, design strength. So coming to each term, mu F, that is a coefficient of friction or slip factor as specified in table 20. So where is table 20? If you go to the next page, that is on page 77, there is a table 20. There the friction values, that is the coefficient of friction values are given as 0.20, 0.50, 0.10, 0.250. So, etc. Depending on the type of surface between this cover plate and the main plate. Okay. So we need to take different kinds of values. Sometimes they'll give directly in the problem. Okay. Take mu f equal to 0.30 or 0.50 or 0.55, etc. Okay. Whatever value given in the problem, you take it, or else you have to assume some value, 0.5 or 0.55, and you should take that value as mu f. Okay. So once mu f is known, so the next thing is Ne. So again on page 76, Ne equal to number of effective interface offering frictional resistance to slip. So look here. So if you look at the screen, so we have covered this butt joint with two cover plates. So how many surfaces of friction we have? Here we have two surfaces of friction. That means Ne equal to 2. In case of butt joint with a single cover plate, there is going to be only one surface of friction or only one surface of contact between the cover plate and the main plate. In such case, Ne equal to 1. Okay. In this case, double cover, so two surfaces. So take Ne equal to 2 and Kh equal to 1, 0.85 or 0.70. So in our case, we always take Kh equal to 1.0 for fasteners in clearance holes. So why do we take that? If you go to page number 73, look at the table on page 73. Depending on the, go to page 73, and depending on the nominal size of fastener, we will have different clearance. So for 20 mm diameter bolt, clearance is 2 mm. If you go above that, it says standard clearance in diameter and width of slots. Standard clearance. If you go to the next column, it says oversized clearance. So if you go to the next column, it says clearance in the length of the slot. So there are three cases. So again, you come back to page 76. KH is 1, 0.85 and 0.70. Ours is KH equal to 1 for fasteners in clearance holes. So, excuse me, in our case, you always take KH equal to 1.0. Next, coming to the formula, you need to find out what is FO value. FO is, if you go down, FO equal to A and B FO. So it is given FO equal to some 3 lines. And on the third line, it gives A and B FO, where A and B is the net area of cross section of the bolt. So what is the net area of cross section of the bolt? So take the diameter of the bolt at the threaded area, never at the shank area. Okay. The reason is, if at all you subject a bolt into tension, if at all it fails along the section where the area of cross section is less. So here, where is the area of cross section less? It is at the threaded area. Okay. So take that area, 0.78 times pi by 4 d square, where d is the diameter of the bolt. So that is A and B value. Okay. Coming to FO, what is FO? Again, if you go down in the code book, FO equal to proof stress, that is equal to 0.70 FUB. Okay. Then what is FUB? That is the ultimate tensile strength of the bolt. If you take 10.9 bolt, FUB equal to 10 multiplied by 100, that is equal to 1000 Newton per millimeter square. So if you are given a problem on this, solving the problem is very easy. You go to that page number 76. So find out what is VDSF. Whatever required to find out VDSF, everything is given. Okay, in the same column. Just pick up those values and substitute the right values. Okay, and find out what is VDSF. That is the bolt value in friction. Okay, whatever the force, design force divided by VDSF, that is the bolt value in friction, will give you the number of bolts. Then coming to gamma MF, I forgot to discuss about that. That is 1.10, again, on the same page, 76, the same column, if you look, gamma MF equal to 1.10 if slip resistance is designed at service load, on 1.25 if slip resistance is designed at ultimate load. So we are not designing any slip resistance for service load. We are going to design at ultimate load. That's why you take gamma MF equal to 1.25. Is it clear to you? So with this, I'm going to end this class and I'm going to continue and I'm going to cover or solve one problem tomorrow. Not tomorrow in the sense in the next class. Okay. We'll meet then.